This is Calculus Unit 1.10 about discontinuities. So in Calculus AB, we're going to fill in two types of discontinuities. We have removable and non-removable, right? The examples of a non-removable discontinuities are either jump or vertical asymptotes. So here's some examples. Here's an equation of a jump discontinuity. And if you notice, in this discontinuity, the left-hand limit and the right-hand limit do not equal. The left-hand limit approaches -1. The right-hand limit approaches 1. When you have a left and right-hand limit that approach different values, that is indicative of a jump discontinuity. Also, vertical asymptotes. Notice that when we take the limit as x approaches 2, our limit does not exist. So usually that indicates a vertical asymptote. And then a hole is one of the hardest, or I guess not hardest, but takes the most labor to find out. So notice that in a hole, the left and right hand limit exist. So the limit does exist, but the value at the point doesn't exist. So notice as we approach 2, the limit is -1. That's what that says. But when you plug into, you get a does not exist. And it's because the original function, right, had a indeterminate form. We canceled out a factor, but still, we don't exist at 2. So this is the last type to test. All right, so here's the graph. Determine all the x values where you are not continuous and classify each as a removable or non-removable discontinuity. So here's the first one. So this is at x equals -1, and we have a jump discontinuity, which is a non-removable. Also, we have at 1, we have a vertical asymptote, which is also non-removable. I'll just put that here. And then next we have our removables, which are our holes, and those occur at x equals 3 and x equals 5. And there is all of the discontinuities. Removable and non-removable. All right, so example 2, it says list and classify the x values where g is not continuous. So we need to find out wherever there's a hole or a vertical asymptote. So let's factor the numerator and denominator. So factoring the numerator, we need to find a number that multiplies to -40 and adds to 3. And that is going to be 8 and 5. And then we need to find two numbers that multiply to -10 but add to -3. And that is going to be 5 and 2, with the 5 being negative. And so let's cancel out what we can. It looks like we have a common factor of x minus 5. So we have a hole at x equals 5. And again, that is removable. And to actually find, if you want to find where the hole is, you can substitute 5 back into here and here, and it will tell you the y value. So this is 13 over 12. So that's where the hole is. It's at 5, 13 over 12. And then we have a vertical asymptote at x equals -2. Again, because we still have we're still undefined here. This is a vertical asymptote. And that's it. And then up here, just in case you wanted to know, this is an x-intercept. Anything that makes the numerator 0 is an x-intercept. So we have an x-intercept at -8. We have a hole at 5, and we have a vertical asymptote at -2. And then the vertical asymptote is non-removable. movable. Okay, and there we go. So example 3, piecewise function. We need to determine all the x values where we're discontinuous and classify. All right, so we're going to have to test a couple points here. We're going to have to test the boundaries. So -2 is where we're going to test. We're going to have to test 1, and we're going to have to test 3. So let's test x equals -2. So let's, again, and if we come back up here, we got to look at limits. So we got to check the left and right hand limits to see if they exist. And then if they do exist, we still have to check that we are defined. All right, so let's start with the left-hand limit. So again, we're going to test to the left of -2, which is this function. And so we're going to plug in -2 into 2 times 2x minus 1, and that's going to give us -5. Okay, so now we need to test the right-hand limit, which we're going to be in orange, and we're going to have to use this x squared minus 9 equation. And in that case, we're going to get -5 as well. So our limit exists. So the limit as x approaches -2 exists at -5. Now we just need to make sure it's defined, and in this case it is. So we got to make sure it's also defined at -2. So we plug in -2 there, and we're going to get -5. So yeah, so the limit exists there, and we are defined there, and they're the same values. So this is continuous. Yes, continuous. So I guess we should say not discontinuous, because that's what we're trying to find. Our next lesson actually is about continuity, and here's a hint. It's this formula. All right, so we're cool there. Let's test 1 now. So let's do our left-hand limit at 1. And again, if we're left of 1, we're still using this orange equation, because 1 on the number line, if we're coming from the left, we're less than 1, so we're using this x squared minus 9 again. So plug in 1, so it's going to be 1 squared minus 9, so that's going to be -8. Now let's do the right-hand limit of h of x. Now again, right-hand limit is going to be this, because we're coming from the right of 1, so we're using this green equation. So let's plug in 3. I'm sorry, plug in 1 to 3x plus 2. And in this case, we're going to get 5. So notice how we have different limits. So the limit as x approaches 1, h of x does not exist. And it doesn't exist because these approach different values. This is going to be a jump discontinuity. Now, lastly, let's test x equals 3. So let's do 3 from the left. And again, if you're coming from the left of 3, you're still in this orange equation. I mean orange. I said orange, but I meant green. So this is going to equal 5. Now let's test the limit as x approaches 3 from the right. And if we're from the right, we're in this purple equation. So plug in 3 to 4x minus 1. And that's going to give us 12 minus 1 is 11. Oh, sorry. This is supposed to be a 3. So this is 11. So the limit exists. The limit exists. The limit as x approaches 3 of h of x is equal 11. Now, just because it's equal to 11, we have to make sure it's defined there. because again, we could still have a discontinuity. Even if the limit exists, we have to check to see if the value exists. And in this case, if you notice, nothing is equal to 3 here. So h of 3 does not exist. This right here is a whole discontinuity. So this is discontinuous and it's a whole. Again, and then example 4 is kind of similar to example 3, but less work. So is it continuous at 2? Let's test. So I guess first off, let's test f of 2. And f of 2 exists. You just plug in 2 here. And you're going to get 10 minus 7, which is 3. Now we have to make sure that the left hand and right hand limit are both equal to 3. Maybe I should have started like that. Start to see if it exists at that point, and then see if the limits exist. Anyway, so limit as x approaches 2 from the left of f of x. Again, if we're to the left of 2, we're going to use this equation here. So I need to plug in 2 into this equation. So I'm going to get 2 squared plus 2 minus 3. And that's going to be 6 minus 3, which is 3. So we're off to a good start. Our left-hand limit's 3. Our value there is at 3. And if we do the right-hand limit of 2, we're also going to get 3 because it's the same equation we used to check if it exists. So this equals 3. So yes, it is continuous. And it's because the left hand and right hand limit exist, and there are 3, and the value at that point at 2 exists and is 3. This is going to be the next lesson about continuity. Last one, find C that makes the piecewise function continuous. So again, we need to check Q of 1. Q of 1 is here. That's going to be 1 minus 3, which is negative 2. Busby. Yeah. All right, bye. Then, so now we need to make sure the left-hand limit and the right-hand limit are the same. So let's do 1 from the left of Q of x. So we're going to use this equation here. Plug in. We're going to get 1 minus 3, which is negative 2. Okay. And then we also need to check the right-hand limit. So plug in 1. So we're going to get 1 squared plus c times 1 minus 5. And if we simplify this, this is going to be c minus 4. Okay, so we have the left-hand limit equaling negative 2, and the right-hand limit equals c minus 4. We already know the value at 1 is negative 2, so we just need to set negative 2 equal to our equation and solve. And if you add 4, you're going to get 2 equals c, and there you go. That's the value that makes the limit exist, or I'm sorry, that makes it continuous at x equals 1.